So we're going to talk about circuits that have resistance and inductance in them. And by the way, all circuits have a little bit of resistance and a little bit of inductance, self-inductance in them. They have to. All circuits form loops, and all circuits have a little bit of resistance in them. So this is true for all circuits. But we have a circuit device that actually dramatically increases the inductance of a circuit. I mean, here's what we did before. I mean, we just had a switch and a resistor. So here's R, and here's the EMF from our battery. And we closed this switch, right? And we said, oh, okay, the current's going to go from 0 to its maximum. And as it's rushing to its maximum current, the current creates magnetic fields, and some of that magnetic field penetrates into the circuit. And so what we're trying to do is create a magnetic field inside here due to this current I. But Faraday's law says, whoa, 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 you're going to get a voltage drop spread throughout the circuit that's going to say, no, I resist you. Okay? I don't like changing current. I got no problem with flux, just don't change my flux, okay? Just back off. And that's why we get a back EMF. And that back EMF we said was equal to negative L, and this is a function of the circuit times di dt. And we called this the inductance of the circuit. Well, I'm here to tell you that if you just have like a 9-volt battery and a Christmas tree light or something, the self-inductance is tiny. Tiny, 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 tiny. And so because of that, the circuit reaches its maximum current, I mean, within a few billionths of a second. So this, so it's insignificant. We neglect it. In fact, that's what we did at first when we were talking about Ohm's law and we had circuits with resistors in it. We just ignored the self-inductance of the circuit because it was worth ignoring. It just wasn't doing anything. Well, here's what we do, though. I mean, here's how I can dramatically increase the inductance of a circuit. I can take this wire with this resistor and I can make a loop out of it. And loop, and loop, and loop, and loop, and loop. Remember we said that L is equal to N times the magnetic flux over the current. We said this before. Well, hey, if I want this to be a whole lot, I just have to have a whole lot of loops, a whole lot of turns of wire. Well, but this isn't very practical. I mean, how can I increase the self-inductance without tracing it all over this rectangle? Well, it doesn't have to be over the whole rectangle like this. What you can do is just take a little part of it and make like this. And just have loop after 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 loop in this one spot. And then come out like that. So, in other words, I just make one little part of the circuit have a huge self-inductance. Well, what do you do? Well, what you essentially do is you take a toilet paper tube. Well, you probably wouldn't use that. You would just use some kind of little tiny cylinder, and you just take wire and you wrap that wire around like this. It is a solenoid. It's not kind of like a solenoid. It is a solenoid. This right here, which I drew kind of in cross section, you just take wire and you wrap it around. It can be a ring. It doesn't have to be a, but usually they spread it out over a cylinder. Now, this is common in cars. It's called a coil in your car, or an inductor. So some of you are taking auto shop. Auto shop, by the way, is really worth taking. So if you go to college and you can take an auto shop class, do it. But a lot of physics in cars. But so we've got this coil, and what it does is it dramatically increases the inductance of the circuit. And so what we call this part of it, well, what did a resistor do? I mean, look, these little wires have resistance to them, right? But they have so little resistance that usually we neglect them, and we put in a circuit element that dramatically increases the resistance. Well, here I've got a device that dramatically increases the inductance. We call this a resistor. We call this an inductor. This is an inductor. An inductor is a device that dramatically increases the inductance within a circuit. Just as a resistor is a device that dramatically increases the resistance of a circuit. Okay? Now, what does that do? What does an inductor do? It allows a circuit designer to control the rate at which current changes within the circuit. Also, it stores energy. It creates a very intense magnetic field, and as we're going to discover next time, we're not going to do it today, but we are actually storing energy in the inductor that we can use later. So we have 3 circuit elements now, well 4. We have the battery, we have the capacitor, and the capacitor stores energy in an electric field. We have the resistor, which removes energy from the circuit. It does work on the outside world. And now we have inductors that control the resistor rate of change of current, and also creates a magnetic field. Because you have a lot of current in there, you're going to have a big magnetic field. And there's energy stored in that field. We're going to talk about that later. Yes?
Okay, so wait, if there's not inductor, do we just assume it as 1? Sorry.
No, if there's no inductor in there, you just assume that the self-inductance is negligible.
Wait, then how do you solve for E sub L?
Well, E sub L would, you wouldn't consider, well, look, think about this. These wires have resistance, don't they?
Okay.
But we neglect them because it's so minor. Same thing is true with the self-inductance of a circuit like this. If the inductance, the self-inductance of the circuit is usually so minor that we neglect it. We just say, hey, the current reaches its maximum essentially instantaneously.
Okay, when we solve for it over here, back in the previous video, basically, we had something where we had to use L. And if
Right.
L is negligible, are we ever going to use this? Or if we ever have to solve for E sub L, how do we get the N?
I'll show you.
Okay.
I'll show you. All right.
Okay.
Now, but before I do that, I want to talk about what's happening here in terms of voltage drops. Okay? I've got a voltage increase here. I come around, I have a voltage drop here, and then I come around, I have a voltage drop, and I'm going to say all the voltage drop is across the inductor. Okay, I'm not all of it. There's the voltage drop across the resistor. I misspoke. There's a voltage drop across the resistor, but all the voltage drop due to inductance is going to be across the inductor, and in that sense, I'm going to neglect the rest of the circuit as being negligible. So here is an equation. I've got E right here minus E sub L minus E sub R. Now, what are these E's representing here? This is the voltage gain due to the battery. This is the voltage drop due to the resistor. This is the voltage drop due to the inductor. Equals 0.
So we have 2 E sub L's?
Nope. This is the battery.
Got that? No, I meant like as
Oh, 2 E sub L's. No, that's what I mean. Okay, look. This is E sub L plus E sub L. Okay, there's 2 E sub L's. No, just wait. This, let's say that this one right here is due to the inductor. This coil that I put into my circuit. This one right here is due to the rest of the circuit. But what am I going to do? Because this is negligible, so I'm going to ignore it. I'm just going to include this one. Now look, I'm doing the same thing with resistance. Okay, look. These wires have resistance, but we ignore them. Why do we ignore them? Because they are so tiny. The voltage drop across these wires, due to the resistance in the wires, is so tiny compared to the voltage drop across the resistance that we just neglect it. Also, it makes the math easier. All right. So, what do we got here? We've got this equation. E minus, oh, you know what? I'm going to switch the order here. This is going to be IR. This is the voltage drop across the resistor. And minus L di dt equals 0. Okay, this is cool. Voltage increase due to battery. Voltage drop due to resistor. Voltage drop due to inductor. Now, can I solve this for current as a function of time? Oh, yes, I can. All right. This is a differential equation. Now, folks, when you've got a differential equation where you've got a variable and you've got the first derivative of that variable, you've got an exponential function. Now, I'm running out of time here and I want to get this done, so I'm going to skip the all the calculus derivations for this.
The only one that makes sense.
Look on page 1007. Go through it. And all of you have had enough calculus where this calculus is easy. So I'm going to do what physics textbooks do all the time. It can be easily shown that if you solve for the current, if you solve this differential equation for current, you will get this equation. I is equal to E over R times 1 minus E to the negative T over tau. But what is tau? No! There's no capacitor in this circuit. It's a different tau. Yes, yes. Down, you savages. Down. Down. Shh. No, look. Look, you guys, your resistance really is futile to this because it's going to be on the test. Yeah. Okay, let's figure out what this tau is, and it's really not hard to do. And this is a great way to rederive it if you forget it on the AP test. Just take this whole thing and divide it by R. So you have E over R. Well, what's E over R? That's current. Minus, this is the maximum current, minus the current at some given time. That's this. And then I'm going to go minus L over R di dt equals 0. Now this has to be in current. This has to be current. Well, I got current here, but I got time right here. Oh, yes. I'm sorry. I got, now, look, this is current. This is current, amps. This is amps right here. What do I got to do? I got to cancel out seconds over here, right? So L over R has to have units of seconds. So tau is equal to L over R. That's my time constant for an LR circuit. Now, folks, hey, this, you can do the same thing for RC circuits. Like if you forget what the time constant is, you divide everything by R and you look, okay, I got to cancel out seconds somewhere, or I have to have seconds. Actually, with an RC circuit, you have to have seconds somewhere. So this is your tau. So you have to wait 5 tau. Now, So this equation is when you turn the when you close this switch up. Let me zoom all the way out. You guys will just have to squint. When I close this switch right here, this is what you get. But, oh, and by the way, here's how I'm going to redraw this circuit. Here's my resistor. Now, here's the symbol for an inductor. I just drew it like this, but the way it really looks is like this. And it makes sense. It's a little coil. Now, here's a switch, and if I have the switch closed like this, this is the equation that describes it right here. But what if I took that switch, and I've reached my maximum current, and I move the switch down here? Okay? If you move the switch down here, you've essentially cut out the battery. The battery is no longer in the circuit. But now you've got this current flowing, right?
Yes.
Well, this current, there's nothing to drive the current anymore. We got resistance, the current's going to go to zero, right? So it's going to go from its maximum, let's say 10 amps, back to zero. Well, what does this inductor do? It says, no you don't. You are not going to change my flux. Change your own flux. So it's going to try to keep the current going because it does. See, here's the magnetic field in here. As this collapses, it's going to try and keep it, but it doesn't win. And what you get is I is equal to E over R times e to the negative t over tau, where tau is L over R. That's your time constant. And we're out of time, so we'll have to draw the graphs for these tomorrow.